Here we have a logarithmic equation. We have three logarithms, all with the different bases, and inside of each logarithm we have a quadratic function. Normally when we deal with logarithms and we're trying to solve logarithmic equation, we try to bring all logarithms to the same base. But that seems to be too complicated, because even if we do that, we're probably going to get some kind of polynomial equation of a high order. So what we're going to try to do here is something different. We will try to investigate what we have on the left-hand side and what we have on the right-hand side. First of all, every logarithm we have here has a quadratic function inside. So let's remind ourselves about quadratic functions and their behavior. So a quadratic function is a function that has this form, ax squared plus bx plus c, where a, b, and c are constants. For example, for the first logarithm, what we have here is a is 2, b is 4, and c is 29. And for the other logarithms, quadratic functions are different. But what we would like to know is how this function behaves when x is changing. If a is positive, the function looks like this, and this function has one global minimum. But if a, the coefficient in front of x squared, is negative, the function goes to minus infinity and it has one global maximum. And the point of minimum or maximum, it can be found using this simple formula as minus b over 2a, where a and b are coefficients of quadratic function. And if we look at what quadratic functions we have here, we will be surprised to find that all those functions have the same point of maximum or minimum. The first function and the last function, since they have a positive coefficient in front of x squared, going to have a minimum at this point. And the second function right here has a coefficient of minus 1 in front of x squared, so we're going to have a maximum. But they all achieved at the same point. But what we have here is not just quadratic functions, but logarithms applied to quadratic functions. This is something that is called composition of the functions. We have a function g of an argument z as logarithm z with the base d, and this d is different for all these logarithms. And this function is applied to function f of x. So z in our case will be f of x. So we will have this composition of the function as g of f of x. And then that's going to be looking like this. So now the question is how this composition of functions behaves. We know how f behaves, how a quadratic function behaves. And now we need to figure out how the logarithm behaves. And logarithm are actually going to depend differently depending on the base. If base is greater than 1, the logarithm is monotonically increasing function. What it means that if the argument increases, so if z goes up, logarithm is also going to go up. And when monotonically increasing function is applied to any function f of x, it really does not change the behavior of that function f of x. Well, it will change the values, it may change slopes a little bit, but what is not going to be changed is wherever function f is going down, g of f of x also going to go down. Wherever f of x goes up, g of f of x also going to go up. So if my f of x looks like this, g of f of x is going to look kind of similar. Wherever f of x was decreasing, g of f of x is going to be decreasing, and wherever f of x was increasing, g of f of x is also going to be increasing. And that means wherever we had a minimum, at whatever x we had a minimum for f of x, g of f of x also going to have a minimum at the same point. Now, if f of x was like this with the maximum, g of f of x is also going to look similar. So wherever f of x had a maximum, g of f of x is going to also have a maximum. And that's a property of a function that is monotonically increasing. Now, if d is between 0 and 1, it's going to be a monotonically decreasing function, which means that when the argument z goes up, log of z actually going to go down. And what happened in this case? Everything switches. If my original function was going down, g of f of x was actually going to go up. And whenever f of x was going up, g of f of x is going to go down. And in fact, if we had originally minimum of f of x, g of f of x is going to have maximum. And if we had maximum for f of x, we're going to have minimum for g of f of x. Now let's just apply our knowledge to all these three logarithms we have. Notice the first logarithm has d greater than 1, so this is the case. Now a here is 2, which is positive, which means that this logarithm is going to achieve minimum at x equals to minus 1. So in the second logarithm, we see that d is 1/2, so we have the second case. And we also know that a equals to minus 1. So we're talking about this function that has minimum at point x equals to minus 1. Now if you look at the third logarithm, d is between 0 and 1, it's 1/5. So we're here. But a is 3, so we're here. So this function is going to achieve maximum at the point of x equals to minus 1. So now what we're going to do, we're going to calculate the value of these logarithms for x equals to minus 1. So the first logarithm is going to give us 3. The second logarithm is going to give us minus 5. So when we add them up, we're going to get minus 2. And the right-hand side is going to give us minus 2. When I derive all these formulas, I use one simple formula, that logarithm of a to the power of b with the base a equals to b. So now notice that what we have on the left-hand side equals to what we have on the right-hand side when x equals to minus 1. Therefore, minus 1 is a solution of this equation. But now let's see what's happening when x is not equals to minus 1. Since we achieved the minimum right here at the point of minus 1, and we achieved the minimum at the same point right here, it means that the sum of these logarithms also achieves minimum at the point of minus 1. And that means that for any other point other than minus 1, the left-hand side should be greater than minus 2. On the other hand, if you look on the right-hand side, and when x equals to minus 1, we achieve the maximum of this function, and that value was minus 2 as well. But it means that for any other x's on the right-hand side, we should get values that are less than minus 2. And what it means that for x's not equals to minus 1, we will not have a single point where left-hand side is going to be equal to the right-hand side. And that means that the only solution we have for this equation is x equals to minus 1.